Imagine walking into a huge office building with no map, hunting for one conference room. At every junction, you pick a corridor, and if it feels wrong, you back up and try another. You're not memorizing data, you're reasoning your way there, one choice at a time. A robot crossing a warehouse, a navigation app choosing a route, a program solving a sliding puzzle. They all face the same shape of task. There's a place you start, a set of moves you're allowed, and a goal you want to reach. We call this whole idea search, and here's the payoff. Once you write a task in this one standard form, a whole toolbox of classic algorithms can attack it for you. So let's build that form, piece by piece. Every search problem is built from 5 pieces, plus a starting state. Learn these, and you can describe almost any reasoning task. There is first, the states. A state is a complete snapshot of where you are, which cell, which city, which board position. The full set of them is capital S. Second, the actions. For any state, capital A of S lists the legal moves. Go north, drive to a neighboring city, slide a tile. Third, the transition model. T of S and it tells you exactly which state that move drops you into. In basic search, it's deterministic. The same move from the same state always lands the same place. Fourth, the goal test. G of S is a simple yes or no. Is this state a goal or not? And fifth, path cost. Each step carries a cost, little c of s, a s prime, and a path's total cost is just those step costs added along the way. Put them together with the starting state, s naught, and a solution is a sequence of actions that carries you from the start to a goal. The best one, the optimal solution, is the one whose total cost is smallest. Now, the single most important distinction in this whole subject, and the one people trip over most. On the left, the state space. It's a graph. One vertex for each distinct state, and an edge wherever a move takes you from one state to another. Here's a tiny one. Start S at the top, goal G at the bottom. The crucial fact. In the state space, each state shows up exactly once. S is one vertex. G is one vertex. That's all there is. A search algorithm, though, doesn't walk the graph directly. It grows a search tree. And a node of that tree is not just a state. It's a state, plus the path used to reach it, plus that path's cost. Node is not the same thing as state. So the very same state can sit inside many different tree nodes, one for each route that reaches it. Hold on to that. In a moment, you'll watch it happen. Here's the graph on the left. Now watch it unroll into a search tree on the right, starting from S. Growing the tree means one repeated move. Expand a node. Expanding a node means generate all of its successors and hang them below it as new child nodes. We start with the root, the initial state, S, sitting all alone at the top. This is depth 0. Expand S. Its successors in the graph are A and B. So the tree grows to children, A and B, at depth 1. On the graph, that's just SS to neighbors. Now expand A. From A you can reach B and G. So A gets to children. Expand B as well. From B you reach A and G. 4 nodes now sit at depth 2. And here is the whole point. Look at depth 2. G shows up twice. A comes back. B comes back. In the graph, each of these is a single vertex. But in the tree, they are separate nodes, reached by separate paths. Push one more level and it gets worse. A's children would sprout their own children. S itself would reappear. And the tree keeps regenerating states forever. The graph is small and finite. Its search tree can be infinite. So how do we search without drowning? With 2 simple collections. The frontier, every node we've generated but not yet expanded. And the explode set, every state we've already expanded. Some call them the open list and the closed list. The loop is short. Take a node off the frontier and expand it. Generate its successors. For each successor, if its state is already explored, throw it away. If it's already sitting in the frontier, don't add a duplicate. Otherwise, push it on. That one rule kills the infinite loops. Run it from S. The frontier starts holding just S. Explode is empty. Pop S and expand it. That generates A and B, which go onto the frontier. S itself moves into explode. Pop A. Expand it. A's successors are S, B, and G. But S is already explode, and B is already on the frontier, so both are dropped. Only G is new. G joins the frontier. A joins explode. Pop B. Its successors are SA and G. Every single one is already explode or already on the frontier. So B generates nothing new at all and simply moves into explode. Watch how the explode set is doing its job. Pop G and G is the goal. Done. 4 expansions. And we're finished. The very same graph whose tree could grow forever collapses to 4 clean steps, purely because the explode set refuses to expand a state twice. And the one knob that changes everything, what data structure the frontier is. A queue pulls the oldest node first. That's breadth first search. A stack pulls the newest depth first. A priority queue pulls the cheapest uniform cost search. Same skeleton, the frontier's order is the strategy. Before we run real examples, we need to know what we're up against, how big these trees get. 2 numbers decide it. The branching factor B, the average number of successors a state has, and the depth D, the number of actions in the shallowest solution. Count the nodes level by level. The root is one node. It has B children. Each of those has B children. That's B squared. Keep going. And the number of nodes at depth D is on the order of B to the D. That little exponent is the whole story. It means the work grows exponentially with depth. Take a modest branching factor of 3. At depth 4, 3 to the 4 is 81 nodes on that level alone. The full tree down to depth 4 is 1 plus 3 plus 9 plus 27 plus 81. 121 nodes. Add one more level and it explodes again. So how do we judge one search strategy against another? By 4 yardsticks. Is it complete guaranteed to find a solution if one exists? Is it optimal? Does it find the cheapest one? What's its time cost? How many nodes it generates? And its space cost? How many it must hold in memory at once? Time and space both live in the shadow of B to the D. Let's make it concrete. 4 cities, A, B, C, D, joined by roads, each road labeled with its distance in kilometers. Roads run both ways. You start at A and you want to reach D by the shortest total distance. In search form, the states are the 4 cities. An action is driving to an adjacent city. The goal test asks, is the current city D? And each step's cost is the road's distance. That's the whole problem, specified. Now unroll the search tree from A depth 0 is A. Expand it. Its neighbors are B and C, so depth 1 is B and C. Expand those and both lead onward to D. So depth 2 holds 2 nodes and both of them are the state D. But they are different nodes. The left one reached D by ABD, 10 plus 12, 22 kilometers. The right one reached D by ACD, 15 plus 5, 20 kilometers. Same state, 2 nodes, 2 different path costs. There is node is not state, right in front of you. The optimal solution is the cheaper one, A, C, D at 20 kilometers. And notice, if we'd stopped at the very first D we reached, we might have locked in 22 and missed it. That's why path cost matters. One more, a maze, a 3 by 3 grid of cells. You start in the top left corner, cell 1 1, and you want the bottom right, cell 3 3. You may step up, down, left or right, as long as you stay on the grid, and every step costs 1. 9 cells, so 9 states. But watch the branching factor change with where you stand. In a corner like 1-1, only 2 moves are legal. On an edge, 3. In the dead center, all 4. On average, call it about 3. The shortest route needs 4 steps, so the solution depth D is 4. Here's 1. Right. Right down. Down. 1-1. 1-2. 1-3. 2-3. 3-3. 4 moves. Cost 4. There's more than one shortest path. Down, down, right? Right works too. Also cost 4. And with B about 3 and D equal to 4, the tree could balloon toward 3 to the 4. 8 even nodes. Far more than the 9 states that actually exist. That gap is exactly the repeated work we're fighting. And because every move can be undone, the state space has cycles. Step 1-1, 1-2, 2-2, 2-1, and back to 1-1. A loop. A naive tree search would chase loops like this forever. A graph search remembers it already expanded 1-1 and simply refuses to do it again. Your turn? Suppose every state in a search tree has exactly 2 successors, a branching factor of 2, and the tree is perfectly full. 2 questions. How many nodes sit at depth 3? And after you expand the root, and then both of its children, how many nodes are waiting in the frontier? Here's the tree. Level by level, the root is 1 node. Its 2 children make 2. Each of those has 2, giving 4 at depth 2. And each of the 4 has 2. So depth 3 holds 8 nodes. That's 2 cubed. The count doubles every level, so the answer to the first question is 8, 2 to the 3. And the frontier? After you expand the root, its 2 children go on. Expand each child, and each pushes on to grandchildren, the 4 nodes of depth 2. The children themselves are now expanded. So the frontier holds exactly those 4 depth 2 nodes. 8 nodes at depth 3, 4 waiting in the frontier. If you saw that the expanded nodes leave the frontier while their children join it, you've understood exactly how the frontier breathes. Nicely done. Trap 1, the big one. The state space is a graph with 1 vertex per state. The search tree is built as you search, and the same state can appear in many nodes with different paths. Never collapse the two into one picture. Trap 2, drop the explored set on a graph with cycles, and a tree search will expand the same states over and over. It may never terminate. The explored set is what makes graph search safe. Trap 3. A solution is a sequence of actions, not a list of states. The states tell you where you are, what you actually pick, and hand back as the answer are the actions. And trap 4. The frontier isn't a passive bag. Its data structure decides everything. A queue gives breadth first, a stack gives depth first, a priority queue gives uniform cost. Change the order, change the algorithm. Let's bring it home. To solve a problem by search, cast it in 5 pieces: states, actions, a transition model, a goal test, and path costs, starting from S0. A solution is a sequence of actions. The optimal one costs the least. Keep the 2 pictures separate. The state space is a graph with 1 vertex per state. The search tree unrolls it, and each of its nodes is a state plus the path and cost that reached it. So one state can appear many times. Search runs on a frontier and an explode set. Expanding a node generates its successors. The explode set stops you from chasing cycles, and the data structure of the frontier, queue, stack, or priority queue is the whole strategy. And judge any strategy by 4 yardsticks. Is it complete? Is it optimal? And what are its time and space costs, both haunted by B to the D? Get these foundations solid, and breadth first, depth first, and the rest fall into place effortlessly.